All right, here we are still on module 5, talking about different components of a computer. And this part here, we're going to be talking about what's inside of your computer, the different components that make up the system. And these are the main components that we'll be focusing on here. So if you go out and you're buying a laptop, or you're buying a desktop or a gaming machine or whatnot, these are the different components you need to be asking about and looking into to make sure you're getting one that fits your need. And we'll be talking about each one of these here in the next few slides. So we'll start off with the motherboard. So the motherboard is what everything is connected to. And on the motherboard, you have a socket that the CPU is placed in. You have slots for your memory or RAM or system memory. Those are all kind of the same thing. And you have slots for it because you can upgrade your memory or add more RAM by taking the old modules out and putting new RAM modules in. Then over here, this disk drive connectors, this is where the hard drive is connected to the motherboard. So there's pins over here that you attach the hard drive to. That's how data gets from your hard drive to your CPU and your RAM. These adapter slots here are expansion slots. If you wanted to add a new feature or upgrade maybe your video card or your sound card or whatnot, you have these expansion slots in here. You have that on a desktop motherboard, not so much with laptops. Typically, laptops are so condensed that it's hard to upgrade anything because they want to save as much space as possible. On the side here, these are all input-output. That's what the I/O stands for, input-output ports, for systems that are built into or integrated into the motherboard. So you can see here you've got sound, you got USB, looks like you got video over here. All those, instead of having separate cards for them in these expansion slots, those are built into the motherboard themselves. Just one thing to keep in mind as you're looking at computers to buy, you cannot upgrade a motherboard. So you want to make sure your motherboard has enough flexibility and the bus speed is fast enough to handle whatever task that you're doing, whether that's video games or working on an engineering project or whatever it is. You got to make sure your bus speed on your motherboard is fast enough to handle that, because you can upgrade RAM, you can upgrade your CPU, you can upgrade other components with the expansion slots, but you cannot upgrade a motherboard. So CPU, we're going to be talking about more of this in the next couple slides, but basically this is, they call it the brains of the computer. This is where all of the instructions get processed and calculations get done. How does the processor do that? Well, this is kind of a little look inside of the components of a typical processor. You have the control unit and the ALU. So this main memory here is RAM, or it might be cache, L1 or L2 cache. So what happens is this control unit goes and fetches the instructions from memory. Goes to RAM, fetches the instructions, brings it back, then decodes those instructions, say, okay, what do you want me to do here? Then hands it over to the ALU, which stands for the arithmetic logic unit. This is the calculator. This is what actually does the math. And honestly, CPUs can only add, subtract, multiply, and divide. But they add, subtract, multiply, and divide really, really fast. We're talking about millions of calculations in a second. So that's what makes a processor so powerful. So the ALU processes the instructions, then sends the results back to memory, to RAM memory, to be used on the screen or however it's supposed to be used. That's how the inside of a processor works. So, and this is just a different representation of what I just said. CPUs, they fetch, decode, and execute. Fetch, decode, and execute. That's what processors do. Then they send the results back to RAM. So here's that control unit that fetches and decodes. Here's the ASLU, and this is the cache that might store common features. Here's another way to look at the exact same thing of how a processor works. And processing speed is determined by three different functions that kind of interact together. First is the clock speed, which we talked about. How many cycles can be run in a second, right? And those are hertz, right? So the faster the clock speed, the more instructions it can process. Also, determining processing power is the number of cores built into the chip. So in this situation right here, we've got 2 cores here, 2 cores here. If this was one CPU, it would have 4 cores. If you go to your task manager, Control-Alt-Delete Task Manager, go to Performance, look at the CPU, it'll tell you how many cores you have. So in this case, I have 14 cores built into that one CPU. It's a lot of cores. That's a lot of processing power. And then, of course, the third function that determines processing power is how much cache you have. This is L1, L2, L3 cache. So if you look at this example here, right, this is a processor that has 2 cores in it. Each core has L1 cache and L2 cache, and they share some L3 cache together. Remember, the L1 and L2 and L3 cache are very small amounts and only store the most commonly used instructions. And then they all still connect back to the main RAM, right? So those 3 functions, hertz, cores, and cache, determine how strong or how powerful your computer is. There's also other features, multi-threading versus hyper-threading. Read that over if you like. It's a little beyond what you need to know for this introductory class, but if you're interested in learning a little bit more, you can read about that and get a feel for it. We're talking about different types of memory in this slide. And some memory is faster than other memory, but the faster it is, typically the more expensive that memory is. So if we look at this kind of pyramid here, the memory on the CPU is the fastest, then followed by the L1, L2, and L3 cache. These are all solid state memory modules, right? Then you've got your physical RAM. So this is your typical RAM that you have in the computer. Then we have virtual memory. Virtual memory is typically memory that is carved out of something else. So you might have a hard drive, and a section of the hard drive is used for RAM. That would be considered virtual memory. Then you have solid state drives. So this is a hard drive with no moving parts. And because it has no moving parts, it moves at the speed of an electron. And so it can go really, really fast. But those are a little more expensive than, say, a traditional hard drive. And a traditional hard drive has the platter with the spinning platter that has the read heads on it. Along with that is optical disk drive. These are your DVDs and Blu-ray discs, which we'll talk more about that here in a few minutes. But again, increase the speed, increase the cost in general. Okay. Now we're getting back to manufacturers of different types of CPUs. So the big players in this game, as far as we're concerned in the United States, is Intel and AMD. Now, with Intel's been around a long time, they've got a lot of different chips. So again, when you're going to buy your computer, you need to look to see what type of CPU they're using. If they're giving you an Atom or a Celeron, these are lower end chips. And in fact, I'll be honest, I don't think they make Celeron anymore. I have seen Atoms out there still. But these are lower end chips that help make the computer cheaper, but don't run as fast. Atoms are specifically designed for laptops and other portable devices, so they save energy. Pentiums are really no longer used anymore, although you'll see some Pentiums in older machines. Right now, Intel chips series starts with an I. So i7 right now, the latest, the time of this recording is an i9 out there. What do you have? Well, if you go to your task manager and go to performances, task manager, control delete, right? CPU, not only we can see the number of cores, but it should tell you the name of your chip. So I have an Intel i7 chip in my laptop here. So go pause the video, see kind of what you have, right? AMDs are also a competitor. Ryzen is their kind of top of the line chip. Used to be used a lot in gaming systems. AMD really made a really good CPU for video games. That they've been kind of surpassed by NVIDIA. So right now, NVIDIA is the big bully on the block. They are making the absolute best CPUs. They started by making GPUs, right? The chips that are really good for processing video games and video, right, in general. But what they discovered was the process they use for video games processing is also really, really good for AI. So NVIDIA in the last couple years has exploded as a company because their chip, and the current one that's really popular is called Blackwell, is a really good chip not only for video games but also for AI. Over here is a list of different manufacturers, the top manufacturers of semiconductors, which is again another name for a CPU or a processor. You'll notice NVIDIA and Intel on this list. I just want to point out Taiwan. So the little country of Taiwan, the island country off the coast of China, makes most of the chips we use, like 80-90% of the chips we use. As you may know from the news, communist China sees Taiwan as part of China. But Taiwan wants to be independent and stay a democracy. China has threatened to attack Taiwan and take it over by force. The question is, would the United States defend Taiwan? Well, right now, we probably would, because if China gets a hold of Taiwan, most of our chips will cease to be able to be accessed, right? It'll really disrupt a lot of our industries. But the last several years, starting the Biden administration, and Trump has continued it, the focus has been to bring chip manufacturing back to the United States. This is a national security issue. If we can't make chips here in the United States, then our economy falls apart. And that's kind of where we are right now. I will also mention this, though. Part of making chips is not just having manufacturing plants, but it's also accessing the rare earth minerals used inside of the chip. And right now, China is doing a great job of controlling and mining rare earth minerals. In the United States, we are hesitant to do that because we have to go into deep in the ocean or underground, which disrupts the environment. And we're the United States very concerned about the environment. We have a lot of rules and regulations that surround that make it harder for us to access those minerals. Other countries, such as China, don't have those laws, and so they're able to get those rare earth minerals. Also, at the time of this writing or this video, the United States has made a deal with Ukraine. We've helped them militarily in their war against Russia. What are we getting out of it? Well, Trump negotiated access to Ukraine's rare earth minerals. So there's maybe an avenue that we'll be able to get some of those because we need our own flow of those rare earth minerals to feed our manufacturing plants in the United States. If not, we could be in a world of hurt if that supply is cut off. All right, let's talk about different types of chips. And we've talked about different types of computers in the past. We have, mainframes, which are really big. We have personal computers, which are kind of desktops that you all use. And then we have embedded computers, very small computers inside another device, like a toy doll. Well, those embedded computers don't need an i7 or, an NVIDIA, Blackwell powerful computer. It just needs something very small. So for those applications, we use a reduced instruction set computer or a RIS chip. And so these are used in very small devices, right? Like Internet of Things devices, and they're very energy efficient. They're not as robust or as powerful as maybe a chip you'd find in a gaming PC, like a Alienware desktop, but they're very energy efficient and can do their instructions very quickly. It's just a little limited in what they can do. All right, so 32 versus 64-bit instructions. This can be a little confusing and really a little beyond the scope of this class, but this is what you need to know about it right now. Think about 32 versus 64. That's how many, say, if you're thinking about an expressway, how many lanes of traffic can travel on a bus, on a motherboard bus system. So if it's a 32-bit system, it can send 32 bits of data or instructions from RAM to the CPU at a time. Pretty good number. But a 64-bit instruction set on the motherboard can send 64 bits of information to the RAM, from RAM to the CPU at a time. So that's twice as much information. So you can kind of see how a 64-bit instruction set is faster than a 32-bit. Along with that, though, the software, whether that be Word, Excel, PowerPoint, a video game, whatever it is, the software has to be written for a 64-bit instruction set. If it's not, if it's written for a 32-bit, it'll still work, but it'll only use half of the space or half the lanes on the bus. Another aspect of 32 versus 64 has to do with memory addressing in the RAM. So in RAM, each kind of cell or spot of storage on a RAM has a memory address to it. And so if it's a 32-bit system, you can only have up to 32 gigs of RAM that it can recognize and process. Whereas a 64-bit system can address up to 16 exabytes of RAM, a heck of a lot more. So that's why you really don't see 32-bit anymore, but it's a concept that you need to be aware of. Here's just another way to express the difference. Right, here's a 32-bit graphic, and here's a 64-bit graphic. You can see there's a lot more detail in the 64-bit because it could handle more instruction sets. So that's just kind of another visual way to see the difference between the two. Okay, now let's move on. All of these components in your motherboard generate heat, especially that processor. That processor, think of it as like the engine of your car, right? The faster the pistons go, the hotter the engine gets. That's why you have a cooling system in your car. You have antifreeze, and you that cools the engine, and then the radiator, the front of the car, takes the wind as you're driving along and cools that off to keep everything nice and cool. In a computer system, the processor here is on the bottom attached to the motherboard. The silver thing with the fins, that is the heat sink, and that draws heat away from the processor and into the heatsink. Then this fan on top blows air through those fins, cooling off the fins. And so this way the heat is dissipated from the processor. If your computer gets too hot, maybe you're out in the sun or whatever the situation is, it'll actually shut down. So at a certain point, and you might have had this happen to your phone too, right? And your phone gets so hot that it shuts down temporarily, gets to a certain spot. So heat can really kill. On some systems that are really, really powerful and the heat generated is really high, you would have a liquid-based cooling system. And so that is similar to, again, your car and your car antifreeze system. You actually have tubes that go throughout your motherboard from one component to the next, and the liquid travels through, gets hot. Then this thing over here is it dissipates the heat and cools the liquid, and then the liquid kind of goes through the different components again. So for really powerful systems, you might have a liquid cooling system. Side note here, a future technology is called quantum computing that is really, really, really fast, but it also generates so much heat that it has to have a special cooling system that keeps the temperature below zero. That's how fast quantum computing goes, and that's how cool we have to keep it in order for it to work. But that is something you'll be hearing. Quantum computing, you'll hear more about that in the next several years. All right, so now we're back on the motherboard and starting up a computer. We've talked about BIOS and post in the past. So post, power on, self-test. When you turn on the computer, it looks at every single component. Oh, we have a mouse. Does it work? Yes. We have a keyboard. Is it working? Yes. Looks at goes through every single component, make sure it's all functioning properly. Then the BIOS allows you to make other changing. Maybe say, hey, instead of booting from the hard drive, I want you to boot from the flash drive, right? And you have security settings and other things in BIOS. A newer version of BIOS is called UEFI. Now, I've heard this pronounced a lot of different ways, but it's UEFI, and it's the modern version of BIOS, where you're able, well, first of all, it has more of a user-friendly interface, so it's a GUI interface, graphical user system, where you can point and click. A lot of times with BIOS, you have to use your keyboard and the mouse doesn't work. But with the modern version, it has a little more of a little better for security and more user-friendly to access. You'll hear these terms kind of interchanged, without much thought. So sort of like, like on my machine here, I have UEFI, but when in class, I typically just say BIOS, and that's not uncommon. So you just have to know, like for a test, is he actually talking about an old version, which is BIOS, or a new version of UEFI? Okay. So now let's look at different types of memory. So there are different types of RAM memory. We've talked about RAM is temporary memory or volatile memory, that it has to be refreshed several times every second. And when you turn the computer off, everything in RAM memory goes away. Now, when you close your lid on your computer, what happens is it takes everything in RAM memory and stores it on your hard drive. And your hard drive is permanent memory. That's why when you turn your computer back on, it pulls that out of RAM, out of your hard drive back into RAM, and you're ready to go again. RAM versus DRAM and DRAM versus SDRAM. It's a little beyond the scope of this class because, again, we're just kind of giving you introductory kind of general knowledge. But just know that, like everything else, there's different types of RAM. If you want to get a little more better look at what your RAM is being used for, open up, go down to your search box here and type in resource monitor. And when you do that, here you go. Here's my resource monitor. It'll kind of show you, okay, this green area here, this is the RAM I'm using. In your task manager processing, you can also see visually how much RAM you're using. So you can see I'm using a lot, and I don't have too much free space. That's also represented here. This blue area right here is RAM that's kind of in use, but being kind of put to the side right now. And then this light blue, this small section right here, this is how much free space I have in RAM. And you never want to use 100% of your RAM because your operating system uses RAM and uses your hard drive to kind of swap out files and move things around. So if you were at like 99% full of RAM, or even your hard drive was 99% full, your computer would have all kinds of issues and weird things would be going on with it. So you always need some free space in there. So again, that's why a lot of times RAM is a bottleneck, because you have more programs opened and in RAM than it can handle, right? Than the operating system can handle. So it's a little bit about RAM. Again, different types of RAM. Don't worry about the differences right now. Just recognize they are. DIMM and SODIMM has to do with the size and shape of the chip. So DIMM typically are smaller RAM modules that go in a laptop. and then other chips are larger chips like this. Okay. How does a hard drive work? So we're saying a hard drive, and this is a traditional hard drive that has the platter that spins and the read head, actuation arm, that reads the data off the platter. How does that work? Well, first of all, the read head never touches the platter. It just, there's like a little millicron space in between the read head and the platter. And it works like this. On that spinning disc or platter, you have circles that are called tracks. You have pie-shaped areas that are called sectors, and then you have sections of a track that are used that are called clusters. So you have sectors and tracks and clusters that store data. How does it work inside? Well, let's take a look at a file allocation system, or FAT. And it works like this. It has somewhere on the hard drive, there's a little table at the beginning of the hard drive that lists every single file that's stored on the hard drive. So here, this file A says, okay, we're going to start at address number 2, and it's going to go for 3 clusters. So here it goes, starts at file number 2, 1, 2, 3. These 3 clusters right here is one file. File B starts at spot 9 and goes for 5. So here's spot 9, 1, 2, 3, 4, 5. So using this table, this file allocation table, or FAT, it records where in the hard drive a particular file is stored. And you can have a file stored at different spots. So if this yellow represented one single Word document, you would notice that part of it is stored here, part of it's stored here, here, and here. And that is not uncommon, because think about, you work on a paper, you save it, you close it, you work on something else, you come back the next day, open it up again, add to it, right? It could be saved on different spots of the hard drive. The hard drive, of course, hard drive platter. Hang on, let me kind of put this back where it was. Here we go. Get it out of the way. A hard drive platter can save on both sides, and therefore the actuation arm is on both sides. You can read from both sides of the platter. So that's how some hard drives can save more memory than others, right? It works by using these magnetic spots here. So each one of those clusters, right, each one of those cells can be magnetized. And when it does, it represents a 1. If it's not magnetized, it'll represent a 0. So that's how kind of the 1s and 0s are represented in a hard drive. Now, you might be asking, gee, if they're magnetized, can I come up with a really big magnet, hold it over a hard drive, and erase all the data? And the answer is yes. This used to be a big issue years ago. Now hard drives are made where they're really protected from magnetic fields. But that's not to say that if you bring your laptop, your hard drive around a kind of an industrial sized magnet, could it disrupt some of the information? Yes, it could. But for all practical purposes in this day and age, you really don't have to worry about that anymore. Let's see, is there anything else I needed to mention here? No. All right, let's move on. So if they just say hard drive, they're just talking about a hard drive. We're talking about one that spins, right? It has moving parts. If they say solid state, an SSD, solid state drive, or SSHD, solid state hard drive, right? We're talking about a hard drive with no moving parts. So this is it's a lot faster. It does not generate as much heat because there are no moving parts. It's quieter and a lot more popular, but it is also very expensive. So, if your hard drive or your laptop or your computer that you're buying at the store has a solid state hard drive, you might be paying a little bit more for it. But the trade off is it'll boot faster and store files a lot quicker for you. So, again, that's a decision you have to make. So, when it comes to optical drives, these are CDs, DVD players, Blu-ray players. How does that work? Well, it works much the same way as there's little pits on the disc, right, on that round disc that you put in your computer or your DVD player or whatnot. Regular CDs and DVDs use a red laser, and so on the spectrum, on the light spectrum, light rays have different thicknesses. And so a traditional CD laser uses a red frequency that has a thick laser or width to it. DVDs can store more data on them because they use a different shade of red as a laser that has a more narrow or smaller light width to it. Blu-rays can store even more data on Blu-rays because they use a blue laser, right? And blue light is actually even thinner than red light. So here's kind of a visual representation. You can see the space in between the bits and the bytes here, and how you can fit so many more bits and bytes using a blue laser because it can get smaller components or read smaller areas. So that's the difference between the optical drives, right? Flash memory, you guys should be familiar with. We've all used a flash drive before. This is a solid state memory, right? SSD. That's why those are a little more expensive. Also, besides flash drive, you use these cards, SSDs or flash memory, for cameras and other kind of peripheral devices, right? As far as video goes, the most common cords for video these days are HDMI. You got HDMI, MIDI, Mini. These are the most popular ones. These down here, Thunderbolt, DVI, are older legacy. VGA is really, really old. You don't really see those anymore at all. But sometimes you see a DVI or a display port. Thunderbolt, you don't see that much. That kind of was an Apple proprietary video cord. So today you mostly see HDMI. And again, here's just some pictures of, these are all more, here's HDMI, and here's some legacy ports that are all used for video, right? And so on video cards, most systems these days have a GPU or a graphical user interface in addition to a CPU. And GPUs, and let me make this, make this a little bigger here, right? So a CPU, right, handles certain type of instructions well, but a GPU handles video instructions well. And the question is, does the GPU have shared memory or dedicated memory? Higher end GPUs will all have dedicated memory, meaning on that GPU, it has its own kind of RAM memory that it uses and stores for itself. If it's a lower end GPU, it might have shared memory, meaning it uses the same RAM memory as the CPU, which there's nothing wrong with that, except you have a limited amount of RAM. So if the GPU is taking up a lot of your RAM, then your CPU can't process instructions as fast. But if you have a higher end GPU and it has dedicated RAM memory on it, then your whole system runs faster. So again, this is just another one of those questions to ask when you're buying a computer, and an explanation of why some GPUs are more expensive than other GPUs. Here's just a visual of how it works. So here a CPU is processing everything, right, the best it can. And in this situation, the yellow dots represent some type of video, or actually AI, right, instructions that a GPU can handle more efficiently. And so they send those instructions over to the GPU, and the CPU does what it's good at. Okay. Then the last one here, we're just talking about different types of sound cards. Most sound cards these days are integrated into the motherboard, and that's good for most applications. If you are into music, or you're in a band and you're mixing together different sounds or whatnot, you might need a higher end sound card. So consider that when you are buying, although most of the time your integrated sound card, it works just fine. Okay, those are the highlights from the second part here. As always, hit me up with any questions and further explanations that you need. Good luck.